Welcome to Lesson 4, Part 1 of Unit 1, Structures and Properties of Matter. This lesson will focus on the models of chemical bonding. If you recall from grade 11, there were 3 models, and the basics for understanding these models is by grouping elements based on electron configuration. We studied before the different blocks of the periodic table, the F, the S, the P, the D, and the F blocks. But also it becomes fairly obvious, and early on in chemistry you learn that the elements are separated into metals and non-metals. Now, based on these premises, there are 3 types of bonds that you learned in the past: ionic, covalent, and metallic bonding. So let's examine them one at a time. In ionic bonding, we have a metal bonded with a non-metal. In covalent, we have non-metal bonded with non-metal, and in metallic bonding, we have metal bonded with metal. So what actually goes on here is that metal atoms lose electrons, becoming cations, and non-metal atoms gain electrons, becoming anions, and they establish electrostatic attractions to maintain the bond, the ionic bond. In covalent bonding, the 2 non-metals atoms have valence shells that are half filled and can form filled shells by sharing electrons. And in metallic bonding, we have metal atoms that have valence shells that are less than half filled, so 2 metal atoms cannot combine, but instead they're going to have a sea of valence electrons that belong to all the atoms, and they move freely. The positively charged ions, therefore, are attracted to all these communal electrons that are moving freely. Here are diagrams. This is a diagram showing an example of ionic bonding. So that's a crystal salt, a table salt crystal made of sodium ions and chlorine ions. In the second part, we have a covalent bonding between 2 hydrogen atoms. So the 2 hydrogen atoms have one single electron that is in the 1s orbital. The overlapping of this orbital is what is going to create a chemical bonding. But for now, we're going to talk about that they're sharing a pair of electrons. And last but not least is an example of a metal. Imagine copper or iron metal. So we have the positive ions surrounded by a sea of electrons that are moving freely. How do we chemists make predictions about the type of chemical bond? So chemists use difference in electronegativity, abbreviated with the delta En. Any difference in science is represented with the Greek letter delta. The difference in electronegativity have a specific cutoff values. So they're going to range from 0 to 0.4, from 0.4 to 1.7, and from 1.7 to 3.3. So these are cutoff values that chemists use to make predictions as to the type of bond that would form between 2 atoms. Bonds with delta En values between 1.7 and 3.3 are classified as mostly ionic. So that would be around here, mostly ionic. Bonds with delta En values between 0.4 and 1.7 are classified as polar covalent. And bonds with a delta En value between 0.0 and 0.4 are classified as mostly covalent. Notice that I added here an extra value, the 0. When delta En is exactly 0, therefore the bonds are classified as non-polar covalent. And they would be the case, for example, of diatomic molecules such as hydrogen and all the different diatomic elements that we study in the periodic table: oxygen, nitrogen, fluorine, chlorine, bromine. Just to clarify a little bit more, in the case of delta E values for hydrogen halides, that's the binary acids, they range from 0.4 to 1.9. Thus, they predict that the bonds are going to be both polar covalent and mostly ionic. So that's kind of a discrepancy here. In gaseous form, these hydrogen halides behave like molecules with covalent bonds. So what this is saying is the presence of other molecules around these atoms affect the type of bond, and therefore when they're in aqueous solutions in the presence of water, they ionize to form acids. So therefore, delta En values are not perfect estimators, but they're good enough for our class. Now let's examine another important concept in chemistry that is has significance in determining the properties of different substances. That's the concept of intramolecular and intermolecular forces. Intra meaning forces that occurs within a molecule or a compound, and intermolecular occurs between molecules. So in the case of intramolecular forces, the type of force that we could have is between an ion and an ion. So between a cation and an ion, the energy is the largest amount of energy per kilojoules per mole per interaction. So this is one of the strongest forces, 400 to 4,000. And the examples are here: table salt, barium oxide. The other type of intramolecular type of force is the covalent force that share electron pairs. That is the second strongest, from 150 to 1100 kilojoules per mole. And the examples are here: fluorine molecule, methane, ethene. The next type of force is metallic. The interaction is between nuclear cations and the CO valence electrons. So that would be the third strongest. Now, as we continue over here, these are interactions that occur between molecules, intermolecular molecules. So we can have an interaction between an ion and a dipole. A dipole is a separation of charges. Remember, there's a molecule that, because of the difference of electronegativity in the atoms, there's not going to be an even share of electrons. So they form a dipole. It's represented here with the delta plus, lowercase delta means slightly positive or slightly negative. So a charged ion and a permanent dipole can result in a very strong type of force. The example would be here a sodium ion interacting with a water molecule. Hydrogen bonding that you explored already in biology, is very important in water molecules as well as in DNA, is the interaction between a polar hydrogen, slightly positive, with non-bonding electron pair that are going to be found on nitrogen atoms, oxygen, or fluorine. So these are the non-bonding electron pair that causes an interaction between what we refer in chemistry as an electropositive hydrogen and an electronegative oxygen. The interaction is moderate, so it's much less, and it occurs between water molecules and ammonia, and between the bases, the nitrogenous bases on the strands of the DNA and RNA. Intermolecular interactions, the third type are dipole-dipole. These ones are permanent dipole interactions. So a polar molecule interacts with another polar molecule. A water molecule can interact with another water molecule. The case here, the example is a hydrochloric acid interacting with hydrochloric acid is moderate. The fourth type of intermolecular interaction is ion-induced dipole. So we can have an ion with dipole induced by an ion. Ion and non-polar. For example, we have the iron ion interacting with the oxygen molecule. The oxygen is non-polar, means the share of electrons is even, and the ion, so that can induce an interaction, is weak. The next type of interaction is called the dipole-induced dipole. It says a permanent dipole with a dipole induced by polar molecule, polar, non-polar. So let's examine here. This is a polar molecule, hydrochloric acid, and this one is non-polar. So a permanent dipole with dipole-induced dipole. So this molecule can induce a dipole, even that this molecule doesn't have a clear dipole. It has an even share of electrons, the valence electrons. However, at any given time, this molecule can induce the electrons to move in a specific direction, and the molecule becomes polarized. And last but not least, we have the weakest type of force, the dispersion, London or van der Waals. Instantaneous dipole induces dipole, non-polar, non-polar. So the example we have in here is argon interacting with an argon. We know that these are not reactive, but they can affect each other by this instantaneous dipole-induced dipole. And then we have another case of C6H14 molecules interacting with each other. So let's look at more in detail these forces holding together the solid crystals. In grade 12, the importance is for students to understand the different type of forces and be able to make predictions as to what would be the different properties of those substances based on the type of forces that hold together the particles. So the type of solids that we study are metallic crystals, ionic crystals, covalent crystals, molecular crystals, and atomic crystals. So in metallic crystals, the particles are metals. The examples are here: sodium, copper, iron, manganese. So what is the metallic bonding? It's the sea of valence electrons that constitute the metallic bond. So the positive ions are attracted to that sea of electrons. That affects the melting point. So metallic crystals have intermediate to high, they're malleable and ductile, and they're insoluble in polar and nonpolar solvents. On the other hand, ionic crystals, the force that occurs between the particles is the ionic bonding, the positive and negative, the cations and anions. So they're attracted by electrostatic attractions between positive and negative ions. And the lattice energy that you study in grade 11 is a measure of the ionic bond strength. Covalent crystals are the force of attraction here is the network covalent bonding. It's an endless three-dimensional network of covalent bonds. The examples are in the small classes or small sizes: the diamonds, the silicon carbides, and silicon dioxide known as quartz. In molecular crystals, there are different interactions, so we have to consider more intermolecular forces such as hydrogen bonding. The polar hydrogen with non-bonding electron pair on nitrogen, oxygen, or fluorine. Hydrogen bonds are weaker than covalent bonds but stronger than B and C. So they're going to be stronger than the dipole and the London dispersion forces. Then we have the dipole-dipole forces. These are present. These are examples of molecular crystals that you see: acetone, ammonia, water, and hydrofluoric acid. This one experience dipole-dipole forces. Those forces act between polar molecules. So all these molecules are polar. They're much weaker than hydrogen bonding. And last but not least, we have London dispersion forces that interact in these kind of molecules. They're the weakest for the small, low molecular weight molecules, but they tend to be larger for heavy or long molecules. These have very important effects on macromolecules that you study in biology, such as fatty acids and long-chain carbohydrates. And van der Waals forces is a category which includes both B and C. So it includes dipole-dipole forces and London dispersion forces. And the example of atomic crystals that we have in here is helium, neon, argon, krypton, xenon, the noble gases. The only force of attraction between them will be the London dispersion forces. So let's summarize. There are three types of chemical bonding: ionic, covalent, and metallic. The bonds form so that atoms become stable and in a continuum from equal sharing to unequal. So the delta En, that is shown over here, is a predictor. If we have values between 1.7 to 3.3, then we can predict the type of bond between those atoms to be mostly ionic, 0.4 to 1.7, polar covalent, and 0 to 0.4, mostly covalent. And if the value is exactly 0, non-polar covalent. Both intra and intermolecular forces affect properties. In particular, they're going to affect the boiling and melting point of those substances. The strongest to weakest forces types are, and I listed them here from the strongest to weakest: ion-ion, covalent, metallic, ion-dipole, hydrogen bond, dipole-dipole, ion-induced dipole, dipole-induced dipole, and London dispersion forces that you can actually review from the table that I presented. So this is the summary for the different models of chemical bonding. In the next sessions, we're going to look at more in detail how different types of bonding occurs, especially for covalent molecules, and talk about the differences between polar and non-polar and the definition of polarity. Thank you.